Okay, so let's just jump right into this with a question that honestly might completely change how you look at the architecture all around you. What if commercial buildings recycled their own heat? I mean, it sounds like common sense, right? If you have heat in one place, why not just move it somewhere else instead of letting it completely go to waste? But the crazy truth is, most buildings do the exact opposite. Basically, most facilities pay a ton of money to remove heat and then turn right around and pay again to create it somewhere else. Just think about the inherent financial and really energetic absurdity of that for a second. We're spending money and energy to literally throw thermal energy out the window, and then we're firing up entirely separate machines to create brand new thermal energy from scratch. It's wild.
Well, today we are going to explore how we actually fix that absurdity. Welcome to This Explainer, where we're going to unpack a brilliant piece of mechanical engineering, heat recovery chillers. This is absolutely our hero technology today. It's a system that's specifically designed to literally turn thermal waste into wealth, completely rethinking how we manage energy inside large facilities.
So, here is our roadmap for today. First, we'll establish the problem of wasted heat. Second, we'll introduce the heat recovery chiller. Third, we'll explore 2 ways to recover that heat. Fourth, we'll cover the golden rule of recovery. And finally, we'll wrap things up with smart controls and priorities. Okay, let's dive in.
Section 1, the problem of wasted heat.
To really appreciate this solution, we first need to look at the invisible conflict that's happening inside modern commercial buildings every single day. It's kind of like a giant tug of war. On one end, you have interior needs. These are spaces that require constant cooling because they're packed with people, lights, servers, or heavy medical equipment. But on the other end, the perimeter of the building desperately needs heating to fight off the cold outside air. Plus, you need domestic hot water and reheat coils. Just picture a huge hospital or a luxury hotel. You might need intense cooling for an MRI room or a crowded conference space. But at the exact same time, literally at that very moment, you need hot water for showers, laundry, and heating the lobby. It is all happening simultaneously. So how do we traditionally handle these competing demands? Well, we use completely isolated systems. A traditional chiller works incredibly hard to pull heat out of the building, only to just reject it all outdoors through a cooling tower system. Meanwhile, a traditional boiler is sitting down in some mechanical room, burning fuel to create brand new heat for the perimeter. We are literally throwing perfectly good heat into the atmosphere while simultaneously burning expensive fuel to make more. Which brings us to Section 2. Enter the heat recovery chiller. Enter the innovation that changes this whole story. So, what actually is it? Simply put, a heat recovery chiller is a system that captures condenser heat we normally treat as total garbage, and sends it to a useful heating load instead of just dumping it out of a cooling tower. The crucial takeaway here is that this machine doesn't just magically create heat out of thin air. Actually, scratch that. It's more like it's a traffic cop. It intelligently captures the heat that's already being removed from the building and just relocates it to exactly where it's needed.
And this fundamental difference completely changes how we evaluate the equipment. A standard chiller is judged solely on how efficiently it produces chilled water. That's it. But a heat recovery chiller, it has 2 highly useful outputs. It gives you cooling from the evaporator side and heating from the condenser side. You just can't judge these machines the same way because the combined value of a machine doing 2 vital jobs at the exact same time is vastly greater than evaluating it on cooling alone.
Section 3. 2 ways to recover heat.
Okay, so now that we know what it is, how do we actually apply it in the real world? There are 2 primary engineering designs used to capture this energy. Application 1 is central plant optimization, where the system is used to pre-cool the condenser water feeding your main chillers. Application 2 is direct production, where the chiller is directly responsible for producing chilled water and useful hot water for specific building loads. Let's break down exactly how both of these work.
Starting with central plant optimization, you can think of this application as the ultimate team player for a massive facility. Imagine a large central plant with several standard water-cooled chillers. By arranging the heat recovery chiller to remove heat from the condenser water loop before that water even reaches the main chillers, you achieve something pretty amazing. You're giving the main chillers cooler condenser water. This reduces their compressor lift, meaning they don't have to work nearly as hard, which vastly improves their efficiency. And the heat that was removed? It's sent straight to the hot water loop instead of the cooling tower. You're taking the burden off the main chillers and the boilers at the exact same time. It's a total win-win.
The second application is direct production. Let's walk step by step through this refrigeration cycle to see how it basically acts like a direct water-to-water heat pump. Step 1. Chilled water absorbs heat from a cooling load, say a really overheated data room. Step 2. Inside the evaporator, the refrigerant absorbs that heat from the water. Step 3. The compressor kicks in, significantly raising the pressure and temperature of the refrigerant. And finally, Step 4. The condenser transfers that highly concentrated heat directly into a hot water loop used for perimeter heating or domestic water. It pulls heat from one part of the building and instantly delivers it to another. Moving on to Section 4, the Golden Rule of Recovery. Now, there is a catch. The golden rule of this technology is super simple, but it is entirely uncompromising. A heat recovery chiller works best when there is a cooling load and a heating load at the exact same time. Without those simultaneous loads, the whole concept basically falls apart. If your building only needs cooling, the machine literally has nowhere to put the captured heat. If your building only needs heating, well, the machine doesn't have a source of heat to recover in the first place. Because of this strict rule, certain facilities are absolutely perfect candidates. We're talking about sprawling hospitals, university campuses, intense laboratories, busy hotels, large high-rise buildings, and central plants that have year-round interior cooling loads. What do they all have in common? They inherently and constantly demand simultaneous cooling and heating. They are always pulling heat out of one zone while desperately injecting heat into another. And this naturally frames the ultimate question that smart building designers and engineers are finally asking themselves. Instead of just automatically throwing heat away outdoors through a cooling tower like we've always done, can we use that heat somewhere else inside the building? Which perfectly tees up Section 5, Smart Controls and Priorities. To answer that question effectively, you need a brain. Depending on the design, these systems can be set up in a couple of different ways. First up is cooling priority. In this operational mode, the chiller runs primarily to satisfy a chilled water load. Basically, cooling is the boss here. It recovers heat only if a useful heating load happens to be available. If there's no heating load right then, the system just rejects the excess heat like a normal chiller would. Heating is just treated as this highly efficient, happy bonus. But on the flip side, we have heating priority. Here, the machine runs mainly to satisfy a demand for hot water. The demand for heat entirely drives the operation, making the chilled water a useful byproduct. You see this quite a bit in large campus networks, where the excess chilled water can easily be piped over to a neighboring building that needs it, even if the primary building doesn't. Now, the reality is the plant sequence here is far more involved than your standard chiller plant. The controls have to constantly monitor a ton of variables. The time of year, fluctuating utility rates, real-time heating demand, real-time cooling demand. The system is constantly asking itself, are we running because we need chilled water, hot water, both? Are the boilers enabled? Are the cooling towers enabled? It requires incredibly intelligent controls to decide what the entire plant is trying to accomplish at any given millisecond. Which leads us to this really excellent point from our source material. Quote, bigger is not always better. A heat recovery chiller needs somewhere to put the heat. End quote. I mean, it's a mic drop statement that perfectly summarizes why you can't just buy massive equipment and expect immediate efficiency. Smart, calculated design, well-programmed controls, and perfectly matched loads will absolutely always trump sheer equipment size. So, as we wrap up this explainer, I really want you to think about the large facilities you interact with, the hospitals, the hotels, the massive office parks you drive by. Keep this provocative question in mind. How much energy is your building throwing away? It is a question that truly has the power to transform our built environment. Thank you so much for learning with me today, and keep questioning how things work.